2006, he joined the University of Alberta and also the National Institute for Nanotechnology in Canada. This research interest concern generally electrochemistry, electrochemical kinetics, and also spectro-electrochemical. And since at least 10 years ago, he focused his research about the molecular junction, and today he will speak about the long-range electron transport in molecular electronic junction with some new and recent results. So please, Professor.
Thank you, Pascal. And I'm certainly honored to be here, and I join everyone else in thanking both the organizers and also all of you for a very interesting conference. It's been very valuable so far, and I hope I can reciprocate a little with that. So, as Pascal said, we're located in Alberta, and in case you need orienting, there's Alberta. And Toronto and Vancouver, in fact, most of the population of Canada is close to the U.S. border. But we're the farthest north big city, and we're rather a long way from Paris. And National Institute for Nanotechnology started in 2002, and the building was finished in 2006, which not coincidentally is when I moved there. And the idea was to have a national lab, which was on a university campus. So it's funded by the National Lab System, the NRC, the province of Alberta, and the university. And the idea was to mesh these two cultures. And the attraction to me is what I'm going to describe to you is having facilities and scientists working in general areas of electronics and how we might put molecules into such things. So you've all seen the history since around 2000 or 1998 roughly of molecular electronics, and these devices all have one thing in common, and that is you're making the molecule part of a circuit, whether it's a single molecule, whether it's a bunch of molecules, whether it's crossed wires, etc. You're passing current through the molecule. And these are generally called molecular junctions. And of course, the big question that I'll try to answer part of today is how do molecules behave as circuit elements, first of all? What are they? I mean, are they wires or resistors or what? And nobody really knew at the beginning, and I'm going to give you some of the answers, at least for our paradigm. So you've heard about diazonium reduction, and thanks again to Dr. Ponson for being one of the innovators here. We make our devices on, I'll refer to it as PPF, but it's sp2 carbon. Philippe said a little bit about it. PPF is just like glassy carbon in structure. Its advantage is that you can make the surface very flat, less than ½ nanometer of RMS roughness. And since these molecules are only a couple of nanometers long, we need to have a flat surface. And the other feature which will become prominent as I continue is the fact that you've got a direct conjugated bond between an aromatic molecular system and an aromatic carbon system, world's biggest pi system, as I call it. And that bond has special properties, not only in stability, but also in electronic coupling, as I'll show you. And really, we were not interested in extending Moore's law here. We were interested in stability. And the reason that the radical attachment is so attractive is that it's a strong bond and is stable to at least 500 degrees centigrade in a vacuum. So we opted for stability rather than worrying about order. And once these things are stuck on, they don't assemble. So it's not analogous to a self-assembled monolayer. Sometimes we make monolayers, sometimes they're multi-layers. We'll start out with 2 to 6 nanometer film, so it's a radical process. So yes, it can form multi-layers. And in a while, I'll show you very thick layers based on the same approach. Okay, well, everybody in this audience knows about modified electrodes, and we were studying these in the late 90s. And the question here was how this molecular layer affects electron transfer to a redox system. And all we're doing is replacing that solution and redox system with another conductor. So certainly the molecule is part of the circuit, and it's not a molecule, it's a couple of billion molecules in a device I'll show you in a minute. And so that's how we're going to address the big question, and that's really the only question I'm going to consider today, is how these things behave as circuit elements, and at the end I'll show you something we might do with that. So just a quick look at the fabrication. This is a PPF pattern. PPF is made by pyrolyzing photoresist, so you can make patterns of quite complex if you like, and then pyrolyze it in a reducing atmosphere. And it's purple because it's a very thin film, so you get interference effects. And in each of those squares that you can make out is a chip, and that chip has got actually 33 devices on it. So we take one of those chips, we electrochemically deposit the layer, vary the thickness by how long we deposit it for, and then put on a shadow mask and deposit the copper and gold on top of that. And so this is the actual device, is that little square. And if you cut through, if you cleave it right through the junction and then turn it out towards you, you can do a cross-section SEM. So this is a 100 nanometer scale now. So this is magnified about 30,000 times from this. And the copper gold layer is not nicely conformal because you have an angled silicon nitride deposit here as the insulator. The molecules are down in here, but since they're only a couple of nanometers long, they're not visible on this scale. NINT, my institute, has got a lot of very good microscopes, so this is a focused ion beam cross-section of that region, and that's the molecular layer. So it's not resolved. It wouldn't be anyway. If you have really good eyes, you can probably see the silicon atoms down here. The carbon atoms are not resolved because they're not ordered, but the interfaces are quite smooth. In fact, if you peel this thing apart and do AFM on these interfaces, you'll find that their roughness is about the same as the native carbon in the first place. Okay, so that gives us at least a visual picture of what the layer looks like, admittedly disordered, but certainly reasonably planar. You can also, if you look closely, there's some contact pads up here, so you can package, oh, there's our molecular layer, I think. So you can package these things, and we make fully packaged integrated circuits. This happens to be a memory device, and it was wire bonded and packaged in a small company in town. Okay, so let's get on to the main question. How does this molecule, nitroazacybenzene, which we chose that because it's a good Raman scatter, so we could characterize it well. And there's a 80 by 80 micron junction right there, and then these black shadows are the probes. This happens to be a 4-probe measurement. We do typically 3 or 4. The electronics are very similar to a potentiostat, and these extra probes correct for the lead resistance. So what does it look like? Well, here's what current density versus voltage, and if there's no molecule present, you get an almost vertical line, and that just represents a short circuit between the underlying PPF and the copper, in this case, on top. And if you had a resistor in there, that's what it would look like. Linear, obviously, ohmic resistance, and a lot of people treated molecules like resistors and thought it should look like that. We didn't know what we're supposed to look like. So we first saw what it looked like in approximately 2003. This is from about 2005 and a little bit more evolved, and that's what it looks like. And what's it supposed to look like? Well, that's it. So the first question the boss asks, of course, is how can you do it more than once? And fortunately, with this paradigm, you got 32 junctions on there that you can test. So if you put all 32 of them on the same plot, then yes, you can reproduce it, and the yield in this case is 100%. It's typically above 80 or 90. The relative standard deviation is about 15%, which is quite good by electronic standards, actually. So we have confidence that this is what it is. Now we have to explain why it looks like that. Couple of properties. Doesn't matter what frequency you're going at, fast or slow. All it changes is the background capacitance as you go to faster scans. Now this is voltammetry, but there's no mass transport. There's no reference electrode. There's no diffusion, at least that we know about. So it doesn't matter what the frequency is, it's symmetric. You can scan at least 10 to the 9th cycles without change. We happened, for a variety of reasons, we happened to try out an old junction that had been sitting on the shelf for 7 years. And we ran it for 4 days straight like this, and it was no problem. So these things are really quite stable. That's the benefit of the diazonium approach, is because you're making a carbon-carbon bond, which is a 4 EV bond, and it's very stable. You can heat the finished device up to 150 for 40 hours. You can run it for as long as you like at 100 degrees centigrade. You can heat it up to 300. So these things are tough, and that was really the reason that we did it this way. Okay, well, Professor Marcus talked about TOEFL plots, so this would be a modern-day TOEFL plot, log current versus voltage. And the question here, I showed this to one of my good friends that many of you know, Mark Whiteman, and he said, well, that looks like activated electron transfer. It looks like a redox process. And yeah, he's right. It's apparently exponential, linear versus voltage, and it looked like Butler-Vollmer or Marcus kinetics. So is this activated electron transfer? Well, that's a pretty easy test in this case because you can cool these things down. And these things can be run down to 5 degrees Kelvin and back up again without changing anything. So you run at low temperature. So this is at room temperature. Just look at about a couple of amps per square centimeter at 1 volt. And yeah, that's a pretty significant current density by electrochemical standard. But remember, we're not really doing any redox processes here that we know about. Okay, this is at 5 Kelvin. And you can see that at 1 volt, we're getting a couple of amps per square centimeter. So it's almost independent of temperature. And if you do the proper Arrhenius plot on it, you find that between 5 Kelvin and 200 Kelvin, it is statistically 0. I mean, it's 0.03, but you can see the error bars. So this is not activated at all. And then there's this little bit of a linear region that looks like Arrhenius behavior. And it may be, but it also is characteristic of Fermi function broadening in the contacts. So you don't need the chemistry to explain that. And a useful number to keep in mind is that if you take biphenyl and think about the ring twist of the 2 rings in biphenyl, that has an activation energy of about 160 MeV. So this is a really small activation energy. It implies that it's certainly not activated here, and it's barely activated here. So in this paper we said you can explain all of the electronic behavior without invoking an activation barrier. So that rules out usual activated electron transfer. Okay, also look at thickness, molecular layer thickness, from a couple of nanometers up to 5.2, which is about as far as we could go at this time with this molecule. And there's a strong thickness dependence. Notice that you go from 3 to 5 nanometers and you got about a factor of 100 change in current. So whatever this is, it's got a strong thickness dependence. So it's not activated electron transfer. What is it? And we weren't the first to consider tunneling, and you're probably thinking that yourself, but that's what it is. And tunneling, of course, says that if you have a solid like our carbon electrode, then it's got electron density that extends out into space. Space could be vacuum, it could be other molecules, it could be a solvent. And that tail is from the Schrodinger equation, says that you have electron density at some distance away from the solid, even though the electron is supposed to reside in the solid. That's the nature of fuzzy electrons that they teach you in PChem. Well, as Albert said recently, yesterday, if you put a molecule or insulator or other things here, you might change the depth of that extension a little bit. It extends least into a vacuum, but you put anything other than a vacuum, different molecules, et cetera, you get a different length dependence, and we'll say more about that shortly. Well, if you have a redox system out here, of course, you can do electron transfer. This is the Chris-Schütze experiment that Professor Marcus mentioned. And you don't have to be in contact with the electrode, you just have to be close enough to tunnel. And you know, the beauty of electrochemistry is that the electron can tunnel across the double layer, which allows you to change its potential over a wide range without affecting the potential of the redox center. And then the electron can tunnel across the double layer. Okay, well, we're not doing this. We did do this, actually, in the 90s, and I'll give you the data in a minute. But what we're interested right now is when you put a metal there. And what this says is that this electron has a probability of showing up over here at some distance away. So that's tunneling across this molecular layer. And if the layer is sufficiently thin, that all makes sense. Okay, well, long before we came along, in the 60s, Simmons in theory and other people in experiments came up with this empirical relationship that said the current density through this thing is proportional to the, it should be, K includes the applied bias, but also an exponential distance dependence. So if you plot log J versus D, then this thing ought to be a straight line with a slope of beta. Beta is sometimes called the attenuation coefficient. All right, well, if you're in a metal, you know, beta is close to 0, so you can go a long way in a metal, and that's a good thing for all electricity and electronics. If you're in a vacuum, beta is pretty large meaning that if you're 1 nanometer away from a surface in a vacuum, you got about a e to the minus 25th probability of electrons showing up there. So it's steep. It's not infinitely steep, but it's plenty steep. Well, okay, we had this thing. Let's take this data and pick a voltage and plot log J versus D at a particular voltage for that data, and this is what you get. So there's NAB, nitroaze of benzene. Beta is about 2.5, which means that say you 0.4 nanometers, you lose 1 over E of the current. And if you do an alkane, which we did with amine oxidation, also developed in University of Paris, with an alkane, you get a steep number. And this is comparable to what Chris-Schütze got for alkanes. This is comparable to what other people, including us, get for electrochemical charge transfer. And the reason is tunneling. And it's always described the tunneling. Sometimes it's get fancy and call it superexchange. And superexchange means that if you have orbitals within this area, it enhances the tunneling probability. And so the tunneling barriers are represented by either by the LUMO, and the barrier is shown here, and that says that if the electron were up here, it would be freely go across. So this represents the barrier for electron tunneling. And you also have a barrier for hole tunneling, which is less obvious, less intuitive, but it says that this electron right here has a finite probability of showing up over here. And so it's actually, this is the barrier that matters in the case of hole tunneling. It's just done in a different order. Okay, so that's a reasonable model, which we didn't originate. Other people had drawn this before. And people had done a lot of work in solution. They got this 8 to 9 for alkanes by electrochemistry, same as us. 2.2 is what you get for aromatic molecules, the same ones actually as we're using here. There are a lot of single molecule experiments to get very similar numbers. So the agreement between those is reassuring. It says at least that we're probably measuring tunneling over this range of 2 to 6 nanometers. It also says that 6 nanometers is not horribly far. It would be if it were a vacuum, but if you got molecules there, then you can get current out to somewhere beyond 6 nanometers, and I'll show you shortly. We're going to go over to about here in about 5 slides, right? So you can go a long way with the right conditions. But of course, the big question, since most of you are chemists, is how do you control this with molecular structure? I mean, clearly you have a difference here between the alkane and the NAB, and so one would think that, gee, you ought to go ahead and try some different molecules and see if this is different. And we naturally did that. And the strategy here would be to pick molecules that have a different HOMO energy, therefore a different hole barrier, or a different LUMO energy. And so that ought to make a big difference. So we did that and had the first sign of some trouble here. I'll identify these in a minute, but these are 3 different molecules that were chosen to have quite different energies. I'll give them to you right now. There is azobenzene, the blue one, and this is what you would draw from the free molecule HOMO, right? 1.4 volt tunneling barrier. Fine, that seems reasonable. But then you go to anthraquinone. Anthraquinone should have a 2.3 volt barrier if you just look at the free molecule compared to the Fermi level of the contact. We measure this with UPS and Kelvin probe. Well, a volt difference, or 9/10 of a volt difference, ought to be huge, yet they're on top of each other. Not only that, the anthraquinone is actually thicker, so if anything, it ought to be even lower than this predicts. Now you take a similar thickness of bisthionobenzene. I'll say a lot more about this shortly. Also a molecule from University of Paris, as I'll mention later. Bisthionobenzene is way up here, so it ought to have a 0.7 volt barrier. So what's going on here? 0.7 volts is less current than 2.3 or 1.4. It doesn't make any sense. If anything, it's backwards. So you can't just look at 3 junctions and make any strong conclusions about this thing. So I say, look, you guys, you gotta get serious, and we got to do a lot of work on a lot of different molecules to try to see what the story here is and see what's controlling transport and what's wrong with our predictions based on these numbers. So we did a bunch of molecules. These are ones you've seen: azobenzene, nitroazobenzene, BTB. We also did biphenyl and things that didn't have nitrogen in them, things like anthraquinone, and the alkane, of course, and it's all explained in this paper. And if you make the beta plot for this, you'd expect, with a 2.3 volt range of LUMOs and 2.4 volt range of HOMOs, they ought to be all over the place by many orders of magnitude. But they're not. And yes, the alkane is different from these aromatics. The NAB is in here, but you can see we got a lot of other data. This is 400 different junctions. Not only is beta statistically the same, with some error, but statistically indistinguishable. Easily distinguishable from the alkane, but not from each other, despite this range. This doesn't include the alkane, right? This is just the aromatics. So not only is beta the same, but the magnitude of the current's the same. Well, this was a dark day in the group, right? Because we're supposed to be doing molecular electronics. And here we're changing the molecule big time and getting the same damn thing. And there are various dark explanations for that fact, but I'm going to show you the one that's true. And we talk about it in great detail in this paper, and it's a very small effect. So something is canceling out this business somehow. So here's what we thought we had, a range from 0.7 to 2.9, or 3 volts of just for the aromatics, and the aliphatic is down here. And this is what we got, 1.3 plus or minus 0.2 volts, and that wasn't just from the transport measurements. We also measured this by UPS, looking at the HOMO offset, and also you did photocurrent measurements on these things, and this is borne out, even though it's not expected. Well, independent determination of these energy levels by other methods agree with these observed Simmons barriers. So what's the problem here? That's the first question. The second question is, how do we do molecular electronics? Well, the story is easily visualized. It's a fairly involved explanation. I'm going to give you the short version of it. But let's consider a molecule that is a model system. So here's our nitroazobenzene molecule right here. And here is a 9-ring graphene fragment, right? This is a small enough molecule to compute on a small computer, it turns out. We've done a much bigger one, but this, I'm just going to show you G9. So we do the standard, chemist B3 lip theory on this, and the key parameter, one of the key parameters here is that dihedral angle. And that probably won't surprise you, because they taught you in organic chemistry that if you want to have conjugation between two pi systems, you want them to be in the same plane. So let's look at this angle and how it affects the orbitals of this system. So I'm going to show you a little movie. It starts with this frame where we calculate the HOMO -1 orbital, and it turns out that that's the orbital responsible for tunneling in this case, right? And we're going to start out with 90-degree dihedral. The equilibrium value for the dihedral angle of the free molecules is 37 degrees. So we're starting out on purpose out of conjugation. And what the movie shows you is what happens is this angle goes down. So that number is going to count down, and you're going to see what changes in this orbital. So you look at this orbital now, and you would say that it's all in the electrode, right? Because the world's biggest pi system is up here. So if you do 54 rings instead of 9, you get the same result. Everything is in the electrode. But now you look at the angle. And as it gets smaller, the orbital extends out onto the molecule. That's a big deal, because you want electron density to show up down here, because that's where the other contact is, right? So as the angle gets smaller, and even when it's at 38 degrees, you still have electron density out here. So what this says is you've got what we've come to call, and I think most of the world calls, strong electronic coupling. You've got orbitals which extend over both, or an orbital in this case, extend over both the electrode and the molecule. Well, all right, that's interesting, but so what does it mean? Well, this is where the copper is. So if you have an electron in this orbital, then it's going to have a finite probability of showing up way over here, even on the oxygens. So that's good. You want to get across this gap. So this is an orbital that's got density on the molecule. And that's important. But to get into this orbital, since it's H-1, you got about a 1.3 volt barrier, it turns out. So strong electronic coupling means that you have interactions between the two systems. And what happens is if you put an electron withdrawing group out here, you pull you pull the HOMO down because it's electron withdrawing, and you get electrons to transfer from here to here, and you can actually calculate it. So you get partial charge transfer from here onto the molecule. And what that does is raise the electrostatic potential of the molecule. This is the same thing that happens in semiconductors. When you put two semiconductors together, you get partial charge transfer until the Fermi levels equilibrate. Same thing here. It's just that as we try to make this molecule different by putting electron withdrawing groups on it, we just have partial transfer of charge. And it's about 5% of an electron gets shifted to the molecule. And that's enough to change the electrostatic potential. And you can actually calculate this, and you can observe it in the UPS and in Kelvin probe. So that's the problem. If all you do here is put substituents on, you're defeated, because the things that you do to change the HOMO level cause this electrostatic shift, which compensates until you get rid of the difference. So it's it's a leveling effect, as we call it in the paper. But there's another question here that I find more interesting, and that is, where does the electrode stop and the molecule begin? You got a big molecule here, and you got all this coupling. That's one system, right? It's not two, it's one. And then out here, you probably also have some coupling like that. So you've got one electronic system here. And you can't talk about separating the electrode and the molecule. Okay, so that's why we were frustrated with this attempt at doing molecular electronics. Now let's get a little bit more farther afield. Rather than just putting substitutions on here, let's ask the question of what happens out here. This is tunneling. What does it do? Does it just keep going? And what happens if your orbitals here begin to approach the Fermi level? Now, there's a question. Maybe it's not barriers anymore at all. So that's what we did. We did it with some help. In this case, the help all came from France. Different molecules and thicker junctions. So first of all, antiquinone, which you can make thick, as the Dasberg group showed a few years ago. You can make it up to 11 nanometers. That's certainly farther than what you saw earlier. BTB is something that the Lacroix group has studied for quite a few years. This is one paper about it. They studied it as an electrode modifier that could become conducting. And you can make it 22 nanometers thick. So we certainly can get past 5 nanometers. Ethynobenzene, you heard about from Philippe Appio and Yann Leroux, and that molecule has got this alkyne group on it, which enables you to do so-called click chemistry to make bilayers. And Yann and Philippe had worked this out with tips, so we tried that and thought that, well, all right, this gives us more variety as to what we can do up here. We put ferrocene in there because the light-size group had reported some rectification for that, so we had some thoughts that it would be quite rather different from just an electron withdrawing group. It's a redox center. And you can see some of the energy levels here. Here's BTB, here's azobenzene, here's antiquinone down here. So those aren't any different. They're still the free molecules we're talking about. Of course, the key question is what happens inside the device. And then this molecule, which is rather recent, and I'm not so sure about it, but we'll have more to say about it toward the end. It's a ferrocene derivative that we can make 25 nanometers thick. Okay, fine. So what happens? Oh, the other thing we had to do, what we did do, was to replace this copper with carbon. And so you can use E-beam deposited carbon. It has the advantage. Well, here it is. So here's E-beam carbon. Here's the molecular layer in the cross-section TEM. Here's the PPF. And then we put gold on top of the E-carbon. And the reason we're using E-carbon is that it can't migrate like metals. It doesn't oxidize like copper. You can tolerate higher bias values. If you go above about 2 volts with copper, it'll oxidize, probably. And it's more stable thermally. So we characterize this E-beam carbon in that paper. Okay, fine. So what do we get? Well, this is looking a little bit more interesting. Notice, first of all, that these are approximately the same thickness, 10.5, 10.2, and 11.3. Notice that antiquinone is nothing on this scale. Ferrocene is quite substantial on that scale. And then BTB is in between. And if you plot these on a log scale so you can see them all, you see that now we're covering big factors. Factor of 10 to the 7th. In a case where before we could barely tell them apart. Now we're getting a factor of 10 to the 7th. And then another factor of 500 if you put ferrocene in there. So now we're talking 9 orders of magnitude range for the same thickness, almost, with different molecules. So that's molecular electronics. And it's because it's thick, and I'll show you why that is shortly. Notice also that this is a pretty good straight line. It's not perfect, but it's better than this one. And if you look closely, you'll see that the BTB is a little bit curved. I'll have more to say about that as we go along. So here's our boring beta 3 line that we saw earlier. here is the click bilayers you can put on top of these, and you don't see much change. Unfortunately, they're too thin. So you see an average tunneling barrier, but since those are under 5 nanometers, and it's published here with Jan and Philippe, it doesn't change much because it's still mostly in the thionyl-benzene layer and only a little bit of alkane and ferrocene. If you go to anthraquinone, it does keep going. It drops like a stone, so you're out at your, this is approximately our detection limit here. And it just keeps going. The slope is still 3. However, here's that NAB, nitroazobenzene, which has a slightly higher HOMO. It's curved. It's straight for a lot of the time, but then it's curved. And if you use BTB, quite different. Let's look a little bit more carefully at BTB and see what might be the origin of that effect. So this is a paper that we did with Lacroix group and Pascal and Maria and Philippe are physicists. And we looked at this quite hard, and the idea was to make thicker layers. And when you make thicker layers, you see qualitatively similar behavior. However, notice that it's still sigmoidal, and before all you saw was this up to 5 nanometers, and now we're going out to 3 or 4 volts and getting these curved things. That's interesting. So it certainly isn't an insulator. But nobody would propose tunneling across 22 nanometers. If you do the log plot, well, these are linear like you saw before. It's not easy to see here, but they are. These are not. So it's definitely curved. It's not a simple exponential. Well, the conventional wisdom is that to get transport across more than 10 nanometers, you need to have hopping, usually by a series of redox events. And that's the standard mechanism in organic electronics, because they're going across hundreds of nanometers typically. Well, if you wanted to test for that, you lower the temperature. So here are 4 of those junctions you just saw at 300 K, and here they are at 310 K. Very little change. So essentially no activation. So this is not redox hopping. Even though we're getting 15 amps per square centimeter across 22 nanometers, it's not hopping. That's actually good news, because that means you got a lot more range to fool around with your molecular structure than you had when you're only at 5 nanometers. So it's weakly activated. So what is it? And next step was Hydrogen Yan, a very good postdoc, came up with this plot for betas. This is log J at 1 volt versus D, and it's not a straight line at all. And he did it versus temperature, and a couple of interesting things here. You do see a range out here. You don't see change here, and that's what we saw earlier. And then in between is a small activation. So actually, he convinced me that there, with a bunch of statistics, that there are actually 3 different beta values. One at the short end, 3 plus or minus 0.3. N equals 8 refers to different devices and different thicknesses, that kind of thing. And then this is in the middle. And then this is at thicker areas. In the thick part, its slope is almost 0. I mean, statistically, it is 0. But if you cool it down, then it goes down to this line. So there is an Arrhenius slope here, and that's about 160 MeV, and that's about the same as bulk polythiophene. So that's acting like a bulk organic semiconductor. It is hopping. Hopping is long range, and that's why they wanted it in organic electronics. That's the good news. The bad news is that it involves radical ions that's got relatively low mobility. So coherent tunneling there and activated hopping here, and then the question is, what is this in the middle, this weird beta of 1? And we talk about this in this paper, and there's a lot of possibilities that I'm not going to take the time to go through. All of these fail. You can make the plots, and they don't work. The only one that does work is called Poole-Frankel transport between traps. Linear J over E versus E to the 1/2. E here is the electric field, not the potential. So this is a plot that at least this electrochemist would never think of making for electrochemistry. Current density versus E to the 1/2. But here it is, log J over E versus E to the 1/2. And the first thing that's interesting is that these guys coalesce. So it's not controlled by thickness, it's controlled by electric field. So whatever this is, it's field driven. You go down to low temperature and it gets even better. This is an excellent straight line. So whatever this is, this equation works at least above 200 Kelvin. Below 200 Kelvin, this shouldn't work because there should be a temperature dependence, and there's not. This thing is flat between 0 and about 150 Kelvin. So Poole-Frankel only begins to describe it, and I'll just give you that Poole-Frankel model. And this was developed for transport between Coulombic traps. So if you have an electron that's in an insulator like alumina, then it finds a positive center and will get stuck there. And that trap has some sort of depth to it in energy. And to get out of the trap, you have to apply voltage, and the more voltage you apply, the more the gap, the more the barrier gets smaller, and you get more transport. So that's Poole-Frankel. And we don't think we have traps. This is the equation if you're interested. We don't think we have traps. I didn't know what the traps were, but we do have molecular orbitals. And we do have a bunch of molecules that are trapped in HOMOs. So how about if the HOMO is the trap? And how about if that's really what is coming out to do transport? So when you apply voltage to that, notice that the barrier height is lower now. And there'll be a point, even at 10 degrees Kelvin, where that electron ionizes, which I think is the right word. You could call it oxidation if you like, but there's no activation, right? No reorganization, at least not before the transport. Then the electron goes across, probably ballistically, because it doesn't have to go very far, and then it gets refilled. So this is a field ionization mechanism. We'll call it molecular field ionization. And its properties are that when you get to a high field, now high in this case is about 10 to the 6th volts per centimeter. So think about that a minute. 10 to the 6th volts per centimeter. If you had your fingers a centimeter apart, you wouldn't want 1,000,000 volts across them, right? But that's what this device is seeing. And there's an analogy to this that some of you probably have heard of. In mass spec, field ionization in the gas phase occurs at about 10 to the 7th volts per centimeter. So we're a little lower than that, but also our trap is much shallower than in the gas phase. The gas phase HOMO is like 5 volts down from the vacuum level. Here we're only 0.35 volts if you do the math. So this is a reasonable idea, and it's field ionization, and it's something that happens when the thing gets too thick to tunnel, but isn't yet so thick that it needs to hop. So if we look at our, I've got one more here to add, this thing. Pharisee. This is a big surprise, all right? And I don't know what to make of this yet. I'm going to show you that it's possible to have a beta which is really quite small, 20 nanometers, and the attenuation is really small, about a couple of orders of magnitude. I'm not sure the structure of this. That's why that question mark is there. We're working on that. We're also working on some other molecules from the Lacroix group that are likely to do this. But the importance of those molecules is to look at the energy levels. And notice that anthraquinone is the lowest one, and it's the one which follows tunneling as long as we can measure it. NAB is up about half a volt higher than anthraquinone, and for whatever reason it starts to bend. And it may be coming over to some kind of a hopping mechanism out here. We haven't done temperature dependence on this yet. And then BTB, which is way up here, is giving us these 3 regions, which we're blaming on field ionization, and ferrocene is the highest of all. So this tells us that when you're above 5 nanometers out of this tunneling regime, things can get really different and really interesting and really molecular. So you guys have all heard this quote, and I agree with Simon in lots of ways, but maybe for us, the bottom here is not so interesting, because everything's tunneling, and because of this leveling effect, even different molecules behave similarly. So I'll call that barrier electronics, and we don't have a whole lot of control over the barrier. That's the message you get from the first third of the talk. However, if you look at the rest of the talk, you got coherent tunneling at that low end. Then you got bulk semiconductors up here where you have a long transport distance. And it does so by redox exchange. And that's good in that it can go 100 nanometers or even a micron. But it's bad because it's low mobility and reactive species. And these are the problems with organic electronics. It's why they aren't ubiquitous, because they're slow and they're unstable. Well, in between, we have other things. Field ionization, which I just showed you. Things like scattering length, resonant transport. So we would say there's plenty of room in the middle. We got a lot of things you can do between coherent tunneling and bulk redox exchange, which have their own characteristics, and some of those characteristics are not produced and not producible in silicon. Okay, so I'm going to finish with a little demo. This is something that Adam Bergman came up with. Adam is my senior guy in the lab. He's also an amateur guitar player. So he looked at this curve, and we wondered, what can you do with this? You know, this technology push, as they say. And he said, we ought to put that in a guitar pedal, a so-called analog overdrive pedal. And I said to Adam, I didn't spend 40 years of science to make guitar pedals. But he said, no, look, there's a reason to do this. One reason is that this is a big deal. This is the number of manufacturers of these things in Canada. Worldwide, there are 200 or more. If you capture 1% of the market for these things, you could fund my entire institute twice. So that got my attention. Okay, well, these things are op amps, not always, but many are. And they have a diode, a pair of diodes as a key component. And I ought to point out that this is 2014 is the 40th anniversary of the paper that everybody refers to, Averham and Ratner, and the molecular rectifier that started molecular electronics, right? Well, this is not a rectifier, but it's going to replace a rectifier. And you can't do this with silicon. And this is the reason it's interesting. This is what the diodes look like, and this is what our device looks like. Much more gradual. And most of you have done Fourier transforms. You know that if you take a sharp feature like this and break it down into frequency components, it's got to have a lot of high frequencies. And those high frequencies are nasty, especially when they're blasting at you at a rock concert, right? We don't have that. We have a gradual shape. So the Fourier analysis is different. This is the waveform you get out of the diodes, and this is the waveform you get out of our molecular junction. And if you do the analysis, you see that indeed, these are the Fourier transform frequencies of the diodes, and they go out quite far because you're almost transforming a square wave, right? Well, so Adam was convinced, and he is convinced, that we should put one of these into our device, and so we did that. So this is a commercial $90 pedal. We took the diodes out, put a couple of connections over here. We're going to run those connections down to a slightly modified molecular junction. There's the actual junction right there. And we put it in a SIM card so it'll be easy to get in and out. You know, we can send it to people. And then don't laugh too loud at the next picture, but this is our elegant laboratory mock-up, right? And so what you do with this pedal is you push down on it. I was pushing down on it. I was using recorded music, but you push down on this, and that switches the molecular junction into the circuit. So what I'm going to show you, and what I'm going to play for you, is what it sounds like. And you're going to have to be the judge about whether this is useful, because I'm not a rock star. Adam listened to this. He took it home, played it on his actual guitar, and wrote me this email in all caps. He said, "This is huge." Well, I don't know if it's huge, but I know that it's different. So what you see here, this is when the molecular junction is off, and then over to the right, at 10, you're going to see molecular junction on. So when it says molecular junction on, the music is going through the molecular junction. When it says off, it's just going straight through the pedal. No diodes anywhere. So hopefully it still works. It worked half an hour ago. And I'll just let you listen to it. It's short. That's off. That's on. That's off. On. Now the reason that Adam said this is huge is what these guys like is they like to shift some of the harmonics up to the mid-range because that way they get away from all that bass. And it's the reason there are 200 vendors is it's terribly subjective what sounds good and what doesn't sound good. Adam is convinced that they've been trying for 30 years to make these things sound better with silicon, and they've tried everything. Nobody's tried a molecular junction. So we have a little company in town that normally sells about 100 of these things, and they're making a prototype which we'll try out. We're going to send around to professionals and let them listen to it, and we'll see. I can guarantee that it's different. Whether it's good or not will depend upon the tastes of the community involved. It doesn't include me. So, these are some of the guys that did the work. There's Adam. These are what I call the transport guys. Jerry was off in London at a conference. And I'll just close by thanking the funding agencies and also the French investigators I've mentioned along the way. And thank you for your attention.
Thank you, Professor McCreery, for this nice talk. And you have just time for one question, short probably, if there is one guy.
Mario.
No?
Something I'm a bit confused about. The effect of the carbon electrode, right, is very big on the molecule. But what about the metal? I will expect the metal to have a bigger effect.
I can give you some empirical evidence that when we change the metal, we've done platinum, silver, copper, and gold by various techniques. It makes a difference, but it's not a big difference. There probably is electronic coupling there too, and ultimately that will have to be included. But I wouldn't say it's dramatic. And in fact, we can even put gold on the bottom, and we still get similar behavior. I wouldn't say it's identical, but similar. That's the good news. The bad news is that a gold substrate is much less stable. I mean, you run it for half an hour and it quits. These things you run for weeks. Or hopefully years if you're playing your guitar, right?
Thank you.
Thank you.
Okay. Thank you again, Professor McCreery. So the next speaker is Stéphane Rigaud.